data, still going to be calculating a lot of stuff and hopefully using our decimals calculator in our iPad to our full benefit. All right, so comparing sets of data. So when we have two sets of data, how do we compare them? It's hard to talk about groups of number and really compare them one to the other. More specifically though, right here, this is talking about if you take a set of data and you transform it. They call it a linear transformation when you do an operation that is performed to the transformation or to the data, that you could write it as a linear function. Okay, so the first type of linear transformation would be when you just add the same number. You add k to every number. So maybe your k is 5, maybe your k is 3, maybe your k is -4, and you add the same number to every value. Let's look at what happens there. Okay, let's look at what happens. If you see example 1, you have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers. Okay, so in those 12 numbers, if you want to take a moment to, it's only 12 numbers, so I'm going to go ahead and do this with my calculator. I have already done it once, so I'm kind of cheating a little bit. So if you want to pause it and take time to do it yourself, you can. I'm going to start with putting them in order because I need to find the median. So I've got, let's see, 2, 4, 7, 9, 9, 10, 12, 12, 12, 14, 14, and 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we have 12 numbers. So my middle number is going to be between the 10 and the 12. So my median is 11. My mode is going to be 12 because that's the one I have the most of. Okay, the mean, you're going to have to punch that in and calculate it. And then you do that, I guess we will probably need our iPad, so plug those into your iPad. And I can do my range though. 15 minus 2 is going to be 13. When you take a chance, you can pause me where I'm at and find the mean, and you can do that right now by punching it into your calculator, into your decimals calculator, and then calculating the mean, and go ahead and calculate the standard deviation. I've already done this once, so I know what it is. So again, pause my video, take and go and do that. Hopefully you're not watching it on the iPad, but you probably are. So see what you can do. Okay. Let's see. So I've already calculated the mean, and I got an even 10, which is nice. My standard deviation was 3.87. All right. So here's what we're going to do now that you've found that. So we're going to add 6 to the mean, to the median, and to the mode, and then leave the range the same. So I'm adding 6, that's going to be 16, adding 6, and so I've got 16, I've got 17, I've got 18. The range, believe it or not, would not actually change if I added 6 to every single number up here. Standard deviation would also not change, because if you added 6 to every single number, you were just taking that group of numbers and sliding it up 6. So your standard deviation, the spread of the numbers, is the same. All right. Now that is one way to calculate it. Another way to calculate it is by actually finding the data value. So if I take every value up here and I actually add 6 to it, that gives me 8, 10, 13, 15, 15, 16, 18, 18, 18, 20, 20, and 21. Okay, I took all my data values in order already, and I've just added 6 to it. If I were to then calculate the mean, punch it into your, you could actually do this in decimals and simply put it in your Y column, in X1 in your Y column. Just plug them in there and then calculate it by putting in your Y sub 1 instead of X sub 1. What you are going to find, well, median has to be obviously 17. The mode is going to be 18 because that's the most. 21 minus 8 is still going to be 13. And the mean, if you added them all up and divided by 12, you would get 16. Standard deviation, you would also get 3.87. Now, 3.87. So you could calculate it either way. You could actually physically add a number to each one, or you could simply add whatever your number, your constant, to your mean, your median, and your mode. Your range and your standard deviation will not change. Okay, well, what happens if we multiply every number by a constant? If you multiply a number, now that's not just going to take that set of numbers and move it up or down like an addition would. It actually multiplies it, so the bigger numbers become bigger. Okay, your smaller numbers become bigger, but not as big. Because if I multiply 2 by 5, I get 10. If I multiply 5 by 5, I get 25. Now my difference is bigger. So when I multiply every number by something, it's going to change every statistic as long as I'm multiplying by a positive integer. All right, so find the mean, the median, mode, and range. So take a minute, pause me if you need to, and punch those numbers into your Desmos calculator, and you can find the mean, median, mode, and range. All right, I'm just going to write them in order. So my median is 19.5. My mode has got to be 20. Actually, not just 22, also 15, because there's 2 of each. The range, 28 minus 11, is going to be 17. And the mean, if you had a chance to do that in your calculator, is 19. Add them all up and divide by standard deviation, then is 5.43. Now, if I were to take the numbers and multiply them all by 5, and if you got a chance, again, do it in your Desmos calculator. You probably already have them written in there. Just make in your Y column, just add 5 to each, multiply each one by 5 and come up with a new data set. But remember, if I multiply everything by 5, these numbers get way bigger really fast. So obviously my things are going to have to change. But everything's going to change by a product of 5, by a multiple of 5. So we are going to take every single one of our numbers times 5. Because when we multiply, the distribution will change. It will not just slide it up or down. It will actually change the numbers. 85, it will spread them out more. 27.15. Okay, so every single number gets multiplied by 5 when you multiply. All right, but what if we're just straight up comparing them? Comparing them, writing a sentence. Yes, I know, we have to write another sentence here. But what if we're just comparing them? Well, it depends. If our distributions are symmetric, if they're both symmetric, or relatively symmetric, we're going to write a sentence comparing the means and the standard deviation because that's how they are centered and spread. Now, if we have 2 skewed distributions, or if you have one that's skewed and one that is symmetric, you're also going to use the 5-number summary. That means the 5-number summary is like the median, the quartiles, or interquartile range, and I'm going to show you how we can kind of incorporate interquartile range without actually saying interquartile range in this example that I have for you. Okay, so let's slide over to the next page and let's look at this first example. Now we are looking at Robert and Elaine both have quiz scores, so they're both in math or language arts or whatever. They both have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 quizzes. They both have 20. I've counted them. It says use a graphing calculator to construct a histogram. I would probably just construct a histogram. I can show you how to do that. It's pretty cool. It's not always super fancy, and it doesn't always look exactly like their examples do, but it is pretty neat. So you can see they already did that for you, and you'll see that they're both symmetric. So if they're both symmetric, very much so, we are going to describe the shape. So first of all, I'm going to describe both of their shape. I'm going to say both Robert and Elaine's, oh, there's an E in there, quiz scores are symmetric. So because they're symmetric, we are going to use mean and standard deviation. So again, pause me while you go to your Desmos calculator and punch in all those numbers so that you can get your mean and your standard deviation for both sets. So pause it. I'm going to go on because I've already done this. So Robert has a mean of 84.7 and Elaine has a mean of 84. But Robert's standard deviation is 7.46 and Elaine's standard deviation is 4.65. So what happens here is even though they're pretty symmetric and honestly their means are very, very close, this tells me that Robert's scores deviate farther away from his mean. So he has a bigger spread of scores. He might score a little lower and a little higher, whereas Elaine, they're all very tight. Not very tight, but closer than Robert's, and that's just it. We're comparing them. So, so first of all, it says justify your choice. I'm going to start with that. Since both have symmetric data, their means, are very close, with Robert at 84.7% and Elaine at 84%. However, Robert's standard deviation, I'm abbreviating, is 7.46% compared to Elaine, 4.65%, which tells us that Robert's scores deviate farther from the mean or are more spread out. Now, do you have to be that wordy? Not necessarily, but it definitely encompasses both their means, and it talks about their standard deviation, and it tells us that while their means are very, very close, Robert's are more spread out because his standard deviation tells us it deviates farther from the mean. Okay? Fantastic. On to the last example. In this last example, we're comparing Kurt's rushing yards for his junior year compared to his senior year, and they already have them in a box and whisker plot, which again, we can do a box and whisker plot on our Desmos calculator. In class, I will probably show you how to do that. It's under the, if you put these numbers in your table, it's under the distribution tab, under functions, distributions, histograms, or histograms and box plots. All right, so this is kind of cool. We have now his junior year. We have it's positively skewed. But his senior year, it's pretty symmetric with the exception of the outlier. But if we have an outlier, we need to use our 5-number summary. And we have to use our 5-number summary anyways because his isn't symmetric, or junior year isn't symmetric, okay? So describe the shape. Kurt's junior year is positively skewed, and his senior year, it is symmetric with a high outlier. Okay, whoops, sorry, you can't see that. So his junior year is positively skewed, senior year it's symmetric with a high outlier. Let's compare these sets of data. Now, if you put them in, I actually did not put them in, but I did find, I put them in order because there's only 12 of them. I found that this median was 19 and quartile 1 was 14 and quartile 3 was 38. This median was 75 with quartile 1 at, oh dang it, 57 and quartile 3 at, oops, 95. All right. So here's how I'm going to actually incorporate that. Instead of actually referencing the fact that my interquartile range is, 38 minus 14, which would be 24, and that interquartile range is whatever, it might be 38, I think. I'm actually going to say that I'm going to refer to the fact that because it's the interquartile range, we know that half of the data points are between there. Okay? I'm going to use that as opposed to using interquartile range. Okay? So, justify because his junior year is skewed, the centers are much different with a median of 19 yards and 75 yards. Also, half the totals his junior year are between, and here's where I'm going to mention my quartiles, 14 to 38 yards, while his senior, he was between 57 and 95 yards. He was consistently higher his senior year. There are so many things you could talk about. Those are just a couple. Another time I looked at this and I was like, well, look here. Do you see how that the entire second year, all of his yard totals are above the third quartile of the first year. And so I actually said something earlier and said that all of his yard totals for his senior year were higher than 3/4 of his yard total his junior year. There's just so many things you could talk about, so many things you could use to compare them. Just make sure you're somehow using the median to talk about the center, and then somehow describing the spread, whether you're describing it by listing your quartiles or by giving your interquartile range. Okay. I know it's a lot of punching in numbers, but it's pretty easy stuff in terms of that. But if you have any questions, come see me.